May I request Anando, please start your presentation.
Yeah, I'm here, and what I will do is I will just start presenting now, and just give me a while. So I have a much simpler task, really, uh, based on some questions that were raised in the WhatsApp group. I felt that 2 or 3 things needed a bit of clarifying. Of course, there were many more things which needed clarifying, but frankly, for shortage of time, I simply can't go on and on. So I will just stick to 2 things right now. Simple things. One of the questions that was asked is, can you do parallel programming in Python? The answer is yes. Let me just sort of give a disclaimer again right at the beginning. I'm getting into the habit of doing that. I hardly ever write very complicated or very computation intensive programs. So frankly, my knowledge of parallel programming has only been at a sort of curiosity sort of level. I have learned about it. I've learned what Python can do, but I've hardly ever used it because I've had no occasion to use parallel programming. That's not the kind of computing I do. Even I don't do computing at all, by the way. I'm professionally a theoretical physicist who does calculations by pen and paper. So computation is really more like a hobby. But as a result, I can't really tell you everything about parallel programming, and I won't even try to. Apart from anything else, I want to give you a demo right now, and I can't give you a demo of the full power of parallel programming on my rather old laptop, which is anyway not great in not too great a state right now. So I've decided to take a very simple example and show you how parallel programming can be done and show that it really works out. Okay, so just a reminder. Okay, I hope everybody can see my terminal right now with a pi for a cause /tilde programs.
Yes, you can see.
I will just start Python, and I will just give a reminder of something Onaboda talked about long time ago. He didn't really mention it in detail in the lecture, but then it was asked later. So I will just mention what this really is. There's a map function. We are going to see a parallelized version of that. That's why I want to remind you of what the map function does. Let's just say I've defined a function which maps. This is not the map. This is just a lambda function, a function defined using the lambda keyword, which in mathematical terms maps x to, say, x cube. And what the map function in Python does is that it takes in 2 arguments. The first one is the name of the function. The second one is an iterable, something whose pieces are such that f can act on them. So I can give 1, 4, 7 or 4, 3, let's say. So the comma in front should not be there. I've given 2 inputs. One is 2 arguments. One is the name of the function. The other is the name of the other is just the iterable 1, 4, 3. And what map does is actually applies f to every one of the elements in the iterable, and so it gives you 1 cube, 4 cube, and 3 cube, and returns the thing in a list. So you've already seen this thing being done in NumPy using NumPy's universal function.
Ananda, perhaps it is Python 2, that is why it is returning a list. In Python 3, it will return a map object, isn't it?
Yeah, right. It will return a map object from which you can convert it into a list and so on. Okay, I'm using Python 2 right now in here. So I could have used Python 3 as well, but anyway, I just started Python. In my machine, Python is by default Python 2. That's an old machine, as I said. Okay, so this is what map does. It essentially produces a new object For Python 2, it's just a list. In Python 3, is something called a map object, which is more useful in some senses, but it can be converted into a list. And basically, it's applying the function on every one of the elements. So this is what map does. The reason why I'm pointing this out is that I'm going to show you what a parallelized version of map is like. But to do that, what I'm going to do is I've just used, okay, let me just open a new terminal, and here I'll show you a program that I've written, which should take a large amount of time. After all, if I'm going to use parallel processing, which means I'm going to essentially use multiple computing units, multiple cores on my machine to calculate things and to speed things up, that actually is going to be useful only if your program really runs for a long time. Otherwise, we will not be able to see the difference. So I just wrote a program which essentially does something very trivial. It imports numpy as np and then defines a function called multi-square root. So what does this do? It says for. Now this is something you have not seen before, but this really means nothing great. It just means I don't care what this variable name is. When I'm using underscore in place of a variable name, I'm just saying that I don't care whether this is I or j or k. I don't want to store it in somewhere. All I want to do is run this 100 times. So what this is doing is taking the square root of x 100 times repeatedly. So basically, it's really taking the 200th root of x, but no, I could have done that directly using the power function, which can take any power, including fractional powers. But I have deliberately done it this way so that the program really slowed down. It's going to take a long time to run because I'm actually running this square root function 100 times. And after that, what I'm doing is simply I'm using standard Python style list comprehension to create a list called results, which applies this multi-square root function x for x in range 1. Okay, this is 100,000. So basically, I will take the 200. What this does is actually stores the 200th root of each of the numbers 0, 1, 2 up to 99,999 and stores them in a list called results. So that's all this does. I'm not even interested in seeing those square roots. I just wanted to show you a function, a program which will run for a long time. So this is one version. This is a without parallelization direct version. I also wrote a parallelized version for this. And the parallelized version is very simple. So I just wanted to illustrate one way of doing parallelizing. There are actually multiple ways of doing parallelizing in Python. There's something called the threading module. There's something called processes. This is multiprocessing. It's one of the many ways in which you can do parallelization. So I've imported this module, multiprocessing. And of course, because multiprocessing is a long name, I have given it a name as MP. I've also imported NumPy, etc. The rest of the program is the same. The only difference is this. I've created a pool object by using multiprocess MP's pool method. So this is really a pool class of objects. There's really not a method. There's a class initiator. Pool, small p-o-o-l pool is a pool object. What does it do? It allows you to essentially pool your resources together and divide your calculation for various places. So the only difference between map in the previous program and this one, there are other differences, but right now let me just focus on this. I'm just using pool.map. So I'm using the map not from Python's built-ins, but I'm using map from this, which is a method of this pool object. And again, just like map, remember this was what I did with map. With map, I had a function name and then a list, or any iterable, anything which will come in pieces. So I did the same thing here. Sorry, this is the wrong place. Where did that go? I think this one. Yeah. So I wrote pool.map. So instead of map, I'm just using pool.map. Name of the function, then the iterable. So just note the connection or the similarity between this call and this one. Map, name of function, iterable. Here is pool.map, name of function, iterable. It will produce the same result, except that it's going to actually divide this huge iterable into pieces and give it to different CPUs which are there on my laptop. My laptop, like most reasonably recent laptops, have multiple processors. This one has 4. So it's going to go to give 4 pieces to 4 processors. And so let's see how that works out. Okay. So now how do I know how long a program takes? I can of course use the time module from Python and see what's happening inside the program. But somebody also asked a question in the WhatsApp group. Somebody who had done programming before asked this question. In Fortran, we used to say time a.out greater than something in Linux. What can we do in Python? Well, let me point out that that time that they were talking about is a Linux utility. It has nothing, or a Unix utility. Used to be a Unix utility which Linux also provides. That has nothing to do with Python or Fortran or anything. You can time any process running on a Linux system using that. So what I'm going to just simply show is that at work. So the way in which I run the program, of course, is forget the time for the timing. The way in which this time underscore square root function is, sorry, test underscore square root. That was the name of my script. Test underscore square root dot py. The way I run it is Python test underscore square root dot py. Well, I'm not sure whether this has ever been stressed in this workshop, because we have either used the interpreter, or in other cases, we have just used some system where you have a button called run, which you click. But I'm pretty sure those of you who use any command line would appreciate that there is a command for running it. We just said Python without anything else. It would open the Python interpreter. If you want to run a script from a command line, you type Python followed by name of the script. And because I want to see how long this takes, I'm going to use a time. There's a time command from Linux itself. So Linux essentially will report back how long the process is going to take. Okay, so I'm just going to run it right now. It's of course going to take some time. Remember, it's actually taking 100,000 numbers and taking the 200 square root of that, and actually doing that by taking 100 square roots, not by calculating the 200th power, which would have been much faster. So now it has given us some information. Please keep in mind what this is. Okay, those numbers will stay on the screen. So we'll try to understand what this means soon. But it tells you that as far as wall clock time is concerned, that is time from the start of this program till the end, there's a real time here. That takes 18.506 seconds, which is reasonably long, so that at least you can begin to see the benefits of multiprocessing. This one is without multiprocessing. There's the ordinary plain Python calculation without using multiple processing. User and sys basically indicate how much of the actual process is taking up of the CPUs. How much CPU is really being used by user part of the program, and the system's part to run this. And the actual answer, the real time here, is a bit more than the sum of these two, because there are some additional input-output issues which take some time. So that is it. So this is basically how much time your CPU really uses. One part from the actual program, the other part so that the system needs to communicate with the program. Of course, it has to write all this huge list into memory and so on. For that, you need some extra time. The real time here is a bit more. But just to illustrate what happens if I try the multiprocessing version. Remember, the program looks almost exactly the same. I just imported multiprocessing as MP, and instead of using map, I used pool.map, the map method which is available in the pool object. And let's see what happens. Again, it's going to take some time, but a bit less. Okay, so notice this reasonable less. This took 18 seconds. This takes only 9 seconds to run, 9.379. So roughly half the time it takes for the program to run by using multiprocessing. Now, why only half? Because despite the fact that I have 4 cores, that's really because, first of all, my cores in the system may be busy. I'm not actually forcing all the cores to use this right now. I can do that by using some other commands. And moreover, this particular program is really one in which calculations are just one part of the whole thing. Input, output, etc. take a lot of time. Network communications and other things. But okay, am I visible to people? Audible and visible?
Both.
Yes, both.
Oh.
Ananda, can you go back to the multiprocessing program once again? Just I have a question.
Okay. Don't ask me very difficult questions because, as I said, I'm not really great at this.
It's a real one.
But let me just see. Yeah. Oops, it's running. Okay, the VI is actually running somewhere else. So let's see. Here.
In this program, why do we need NumPy? I can't see that.
Don't.
Oh yeah,
We don't, except that the square root.
Doing it on the entire thing. Yeah, okay.
I borrowed the square root from NP. I could have taken it from math. That would have been roughly the same speed.
But instead of using the NumPy, if you use NumPy already reduces some time, right? And then you are using multiprocessing.
But I'm doing that for both of them. I'm doing that for both of them.
Yeah, the reduction of
Remember,
time is
without
for both using NumPy and multiprocessing, right?
Yeah, you're right. You're right. But I'm not actually using NumPy on an array. I'm using NumPy only on a single number, which essentially means. So I'm not really using NumPy. I could have just used import math and use the math square.
Can't we see that? Just remove the NumPy and use it.
It will not make much difference. It will just we'll just put this. Okay, good. Let's see. Of course, the comparison between the two programs, math.sqrt. So what Onabuda is saying really is NumPy already does a bit of multiprocessing on its own. So maybe that's showing up here. Let's see. Well, this works even faster, right? It took only 1.613 seconds. So why did that happen? That's because I agree that it works a lot faster. That's simply because the math square root is actually better at calculating square roots of single numbers than the NumPy square root is. The NumPy square root essentially has to decide first whether it has been given a single number, and here is going to decide that actually 100 times 10,000 times. So it first checks whether it has a single number on an array, and then there's a single number routine. So mass square root actually is faster if you give it a single number. And I'm pretty sure if I did that to my test program as well, test square root, the one without parallelization, yeah, now you see the real problem is this. What we have is a program which runs too fast. Okay, that reminds me. The reason why I used NumPy really was a bit underhand. I would have to actually increase this a lot more to begin to see the real advantage between multiprocessing and not multiprocessing. You have to realize one thing. Multiprocessing means that all the other communication has to be with various cores, right? All the other cores, other thing. So the communication takes a lot of time. So whatever you gain by breaking up the thing, but let me go back a bit and then so that I can perhaps do better even on this by doing this. So here, what I can also do is add a add an argument which says how much of the iterable will I break up into and give to different processes. So I'll make a conservative value. Let's say 100 pieces of the iterable, 100 elements will go to each processor. And let's now try timing this. Yeah, so now that I've changed the default value and chosen some number, I can play around with it and I will get perhaps better performance. So you see, this was without multiprocessing, 1.6 seconds only. The reason why I now remember why I chose an NumPy. I chose NumPy X simply because it's slower. It takes longer time. And that's besides, that may sound strange because NumPy usually is a lot faster, but it's a lot faster when it's acting on arrays. It's actually slower when it's acting on single numbers. It's not meant to act on single numbers, actually. The reason why I did that was that unless the program runs for a long time, you cannot really see the advantage of multiple processing. But here you can see a bit of it. The real time is 1.6 seconds. Here, multiprocess version shows 1.28 seconds. But I would also draw your attention to one thing. The user time, the actual time which the CPUs are being used. Notice here, to add the user time to the system time, you get 1.05 seconds, which means quite a substantial amount of time is being spent outside the CPU in reading the program, then writing to memory and so on. But here, this seems even stranger. The CPU apparently is using 1.88 seconds, whereas the real time is of course 0.1282 seconds. So how can the CPU be working for longer than the actual program is taking? The answer, of course, is that this one is the sum total of all the CPU times together. Because my program is breaking up into different CPUs, and the sum of all those times taken are being returned, this really means that I'm actually making the CPUs work a total of 1.88 seconds to work out the thing. But it's actually only taking 1.28 seconds to return the result. Okay. So the point is, if you want to do multiprocessing properly, you will have to delve a lot deeper into this. I just gave you a very quick view of what can be done. In fact, the map is one of the least efficient ways of multiprocessing in Python. There are many other much more powerful parts, but that would take at least say one whole session to talk about. I don't really want to do that. the question came up, how can we use multiprocessing? The answer is yes, and I just wanted to illustrate that. If you really want to do multiprocessing seriously, you'll have to study this up, and there are plenty of resources available on the net which will tell you how to do this. But it can be done. And of course, if you're using a trivial program like the one I have used, you will not get much of an advantage. Only if your program is very strongly computation dependent, and also when you know how to break it up so that you can give to different processors. So quite a lot of study has to be done before you can really reap the actual gains of multiple processing. And okay, I also in passing showed you that you can use the time function the same way you use for Fortran or anything, because time actually has this time, not the Python time. This one has nothing to do with Python or Fortran or anything. This is just a Linux command which will tell you, give you Linux times. If you really want to time your program, it's better to actually use a time module and really work inside. Whether parallel programming can be applied to machine learning? Of course it can be. In fact, it is. By the way, as Onaboda pointed out, NumPy actually uses a lot of parallel programming by default. You don't even have to code it. When you're running a NumPy program, it tries to take advantage of however many cores the system has. So if you, by the way, if you actually tried speeding up a NumPy program by using multiple processing, usually you might end up slowing it down. If you are on the other hand, if you have multiple computers in your hand and you have joined them together to form a cluster, then you can use the multiprocessing thing efficiently. NumPy will automatically use multiprocessing within your own machine, so you don't really need to write any further multiprocessing for that. Okay, so this was what I wanted to talk about here. And there's another topic. So how long do I have? That's the question that I want to ask.
You can continue.
Yeah,
I think you have time.
Not as long as yesterday, right?
Yeah. No, I think. Yeah. I mean, after this session, we don't have much to do. I mean, there's a few formal things.
Question answers, right?
Yeah, enjoying your talk.
Okay, so the next thing I will actually seek Unaboda's permission before I do the next thing. I thought from some of the comments made that his discussion on object-oriented programming became a bit difficult for people to follow, basically because at the end of the day, also because the particular module or particular class he wrote. So I think I can see a question like, what about multi-core machines? Actually, I'm using a multi-core machine. Nowadays, almost every machine is a multi-core machine. So if you use NumPy on a multi-core machine, NumPy will take advantage of multiple cores anyway. If you want to use multiprocessing, if you are using NumPy, you won't really gain much on a single multi-core machine. On multiple multi-core machines or multiple machines, you will gain. So these are issues which are, of course, very technical and only useful for people who actually write very complicated and long-running programs. Trying to use multiprocessing in simple programs actually usually end up making things worse, because pieces of the data have to go to different processors and come back over communication, and that communication takes a lot longer than the advantage you get from multiple machines. Okay, now as I was saying, Onaboda talked about classes, and he illustrated using a vector class, which actually is very, very useful, and it was very nice. But I thought that I could perhaps explain that once again a bit, because not the vector class, but I would use a very simple class to illustrate some basic ideas, so that
yesterday talk also you use network class.
Yeah, I use a network class, but I hardly ever. That's really why I wanted to talk about this, because I hardly describe what the class or what these things inside are. You already talked about that once, but maybe repeating that might be useful.
Okay. You just explain it once again.
So I want to take an example which I think everybody should be able to follow, because I would just use And again, this is an example for which the class actually exists in Python. So I am really reinventing the wheel in a way. But let's just pretend that Python did not have a way of dealing with rational numbers, right? So what I'm trying to do is create a class which, for example, if I put in 3 by 5 plus 2 by 3, it will actually do the kind of primary school calculation. That is 2 times 3 is 6. Put that in the denominator, put the numerators together, and return a rational number to me, some ratio. Okay, so everybody here, of course, knows what a rational number is. It's a ratio of 2 integers. And I'm going to essentially show how to write a class which implements that. So maybe I'll just write a module here, a Python file, which will have the class definition in it. So class so as Onaboda said, when you want to create the myrat, of course, here is the name of a class which is essentially a blueprint. It's a design for an object, and an abstract design. When I actually create an instance of the class, then I will essentially get a real object to play with. And for that, a program that is always called at the very beginning, the first program method, it's really called a method, not a program, but function. Sorry. The first method that you should have in a class is something called underscore underscore init underscore underscore. That's the convention. You may actually give some other name. It doesn't really matter. But usually everybody in the world calls it this. Although what you call it is different. Some people call it underscore underscore init underscore underscore. That's a big mouthful. Very often people call D double underscore, D init double underscore, or the people who use it very often, they just call it dunder. So these are called dunder functions. Dunder for D double underscore. So dunder init, of course, is a lot smaller a name. Strictly speaking, this is dunder init dunder, but people usually call it dunder init. That's a standard name used in object-oriented circles. And here, so what you need to do is put this self is basically the name of the object which is going to be created. This is the object itself, and that argument has to be always given. And here, let's just say I'm going to give an extra tuple as the input. So and let's just keep things very simple for ourselves right now. I'm assuming that this is a tuple, and I'm going to unpack the tuple which has 2 integers in it into A and B, and just define these attributes. And we are done. Basically, that means the moment I create a myrat object, what I'm going to get is basically I'm going to call it with a tuple, and the 2 parts of the tuple are going to go into 2 attributes called self.num and self.div. That's it. And just for later ease, what I'm going to do is also define an attribute called a pair. Okay, but this is very trivial, but you must realize one thing. Suppose somebody gives you 4 by 2. Do you really want it to be 4 by 2? Or you would want it to be 2 by 1? Or maybe somebody gave you 15, 21. So that means you're trying to write 15 by 21, but we would all agree that instead of talking of 15 by 21, I would cancel the 3, the HCF, and then once I cancel the HCF, I should get 5 by 7, right? So instead of doing this, what I should do perhaps is first calculate the HCF of A and B. And then, instead of so A, instead of this, I would have this, right? So this is the only tricky thing here. If somebody gives you an input which tries to create a rational number with 15 in the numerator, 21 in the denominator, I would expect my computer to realize that this is actually 5 by 7. Of course, for this to work, I need to have an HCF function defined somewhere, preferably in this module itself. So I will do that. But just before I go there, let's just put in some interesting stuff together. This actually is these Dunder functions, in this case, Dunder representation. This one decides how the object is going to be represented when you try to print it out or when you display it on screen. So basically what you do is self has a self.pair object. It also has self.num and self.div, which are just individual pieces. So what I can, of course, do is something like this. Instead of printing, I will just return. This is a method. So what it does is returns a string. The string is simply two integers. So I'm not sure whether this has been talked about before, but this, anybody who has done C programming would definitely know this. And all we are saying is these %d stand for integers in a string. So this is a substitution. It takes the elements in self.pair, unpacks them into the two places and just puts them in. That's it. And let me just add one more method to this, just add. So I want to return by when you add two rational numbers, that's what self and other are going to be. Once again, you don't have to call them self and other, but that's the rule. Everybody in the world calls them self and other. Self breaks up into numerator P, denominator Q. Other breaks up into numerator R, denominator S. And what I want to return is a rational number is formed by the tuple. The denominator, of course, is just R times Q times S. Numerator is simply P times S plus Q times R. And you're done. Sorry, Q times R. Okay, I will not lengthen it any further. Of course, if you want to really make this a real-time rational class, what you need to do is put in things for subtraction. That's underscore underscore sub underscore underscore. So these things override the minus sign when you actually use it in your program. Then you could have mul underscore underscore mul underscore underscore. You could have div and so on. Of course, one thing I need to really at least make this work, which is define HCF function. But can anybody tell me what this really is? This line, what will this do? I hope everybody remembers that a percent b is a remainder when you divide a by b. So can anybody tell me what this is? What this does is starts with two integers a and b as the input. As when you say while b, while is a loop which maybe we did not show you in this sessions, but while is also another kind of loop. It runs as long as the condition here is true. Now, typically when you write while some condition. But remember we said a long time ago that when you are dealing with numbers, all non-zero numbers are taken as true and 0 is taken as false. So this really means that as long as b is not 0, keep on doing this. Okay. So while b is non-zero, it's going to keep on happening. So what is happening here is you take the numbers a and b, you actually replace b by the remainder which you get when you divide a by b, and replace a by b, which essentially is something you all learned in school. There's something called the Euclid algorithm for calculating the HCF. You just repeatedly take remainders and divide, and then use a remainder as your divisor and keep on going until you don't have a remainder any longer. And the last number you're left with is what is called the a highest common factor. So the so-called Euclid algorithm in maths. All we have done is using the packing unpacking facility of Python. Remember what's happening here is you're taking the numbers b and a and calculating b comma a percent b, this tuple on the right hand side. So they're being packed in a tuple, and now they're being unpacked into a and b. And this is going to keep on going as long as b is not 0. So as long as the final thing, finally, when will b become 0? B is really a percent b, right? What used to be a percent b in the previous step. B becomes 0 only when a divides b. That means you have reached the end. And then a, which the last b was, the one before, the step before that, that actually what your HCF is. So let me just show you how this works. I hope I've typed everything. Okay, so this much. Anyway, I hope I will just get through this before this gives up on me. So I have this module. Wow, it's really slow now. So I imported the myrat module, and inside the myrat module there's this myrat class. So what I do is create an instance of the class by giving a tuple, let's say 4, 3. Oops. Oh, I'm pretty sure people may have realized what happened. I've imported the myrat module, But inside the MyDat module, there is the MyDat class. So this comes of using the same name twice. I forgot that I did not import the class. I imported the module name. So it's MyDat.MyDat with this. So now if I want to see what R1 looks like, that's where the under representation comes in. Okay, I mistyped, right? I must have put in the wrong slash. Did I? Okay, let me just check. Okay, here in the representation, yeah. Unfortunately, I put in the wrong slash here, which is why this is looking a bit crazy. It's looking for the ulta slash 3. I meant the actual slash. But anyway, as long as we have done this, you should sort of bear with me with this. So let's just try another one. Okay, first of all, let's see whether our escape really is working. So as I said, 1521. Let's store that in R2. Let's see what R2 is. You see that HCF of 3 has been calculated, has been taken over 5 by 7, and so on. So apart from modulo the stupid mistake I've made of using the wrong slash, it seems to be working. And just finally R1 plus R2. Well, you should be able to check that if you added 4 by 3 to 5 by 7, you actually get 43 by 21. So I've sort of created that, but if I tried R1 minus R2, then I get an error because minus has not been defined. I have not defined the dunder sub dunder thing for my particular class. I have not defined how to multiply, etc. I can always keep on adding those classes and making this into a more and more rigorous thing. In fact, of course, I could also ensure that I can add an integer to this. I can, if somebody tries to give an integer, for example, right now, if I try this, my thing has really gone slow now. Instead of this, suppose I try to give this, of course, is a rational number, right? Let's try this, I'm going to get an error. Oops, I made a mistake again. Now I'm getting an error because, after all, in the very first step, it took the argument, tried to unpack it into pieces. But I've given it an integer. The integer, of course, what is complaining is integer is not iterable. It can't break an integer into pieces. So, of course, if I wanted to write a proper rational module, rational class, what I would do is take those cases into account. So if somebody gave an integer as an input, how to handle that, how to add an integer to a rational number, how to multiply, how to divide, all of this. But this can be fleshed out. But the basic idea is the moment I create the class object, I now have an object which has attributes like for example, if I want to check what r1.num is. And take it, yeah, that's just 4 because r1 is my 4 by 3. I have the attribute dev denominated. Looking at help here so that I can't, it's just telling me
Anando, we can't hear you.
I could
Anando? I think audio is the problem. Anando, we can't hear you. Can you reconnect? We are running short of time. Uh,
In the meantime, I want to give an answer to class abstract. He asked that in commands we are not explicitly writing the name of the method. We are using underscore underscore. I mean, there are some special names like underscore underscore add underscore underscore. If you write a method by this name, if the name of the method is say underscore underscore add underscore underscore, then this method can be called in two different ways. You can call object dot underscore underscore add underscore underscore, the typical method of calling a method, or you can use a plus sign. So that is a special method name reserved for overruling the connotation of a plus sign. Similarly, the connotation of my star sign you can change if you have a method called underscore underscore mul underscore underscore. Is it clear?
okay. I think Anando's talk is almost over, and we have no time. Actually, we have no time for discussion. And now I request Arunaboda and Abhijitda
uh, um, Class abstract. The question is, it is not underscore underscore RPR. It is underscore underscore REPR. Is underscore underscore. Yeah. This is the method which will run if you just say the object name and enter. Right. If you just say the object name and enter, what will happen? Then it will call. It will search for a method which his name is underscore underscore REPR underscore underscore. If there is a method, it will execute that. And it's therefore it is always better to keep such a method that if you just type the object name and enter, what will happen?
uh, let's thanks to Anando. Even on the last day, he delivered a beautiful lecture. And now this session is open for discussion. Please unmute your microphone, even turn on your video and ask any questions. Our experts are here to answer your queries. Thank you.
Yeah, we are very scared. This is a very scary situation.
Yeah.
Please.
Well, I am back, although I'm not sure how much of
Hey, Abhijit,
my
Anando is back, so we are relaxed.
no, no, how much of I'm not even sure how much people heard and how much didn't because my machine froze on me. That's what I was worrying about. And
Actually,
it just
we
died.
have.
But I think Arunabha picked up, right?
Anando, would you
Arunaboda,
kindly pull the curtain? I mean, I
No?
can see your face, but there's a lot of light coming from behind.
Oh, you don't need to see my face. I need to switch off my camera, I guess.
Anando,
But anyway,
we have started our discussion session, and
yeah, right. Yes.
we are
Even
asking
even
people.
I by saying now we can start our discussion session perhaps. Then I
Yes.
realized that I have not been audible for I have not been connected for the last 3 minutes or so.
Okay.